Welcome to this webinar organized by the Sustainability Working Group of E-SWAN. This webinar will open the second season of our webinar series dedicated to discussion and reflection on the sustainability of our space weather activities. You may find the previous webinar on the E-SWAN YouTube channel. And today we will talk about the life cycle assessment of a space mission with a particular focus on a concrete example given by the assessment of the X-ray integral field unit instrument on board the ESA Athena mission. I'm Véronique Delouille and I will be your host today. It is my great pleasure to welcome Andreas Wolnievik. Andreas completed his master's degree in space engineering at Luleå University in Sweden in 2024. Between 2019 and 2022, he contributed to the ASTER project, which launched a sounding rocket as part of the Rexus program during 2023. And while in Sweden, Andreas worked at Swedish Space Corporation with the rocket and balloon launch team, and also at LKAB, a company at the front edge of the green transition within the iron industry. In 2021, he also went to South Korea through an exchange program and studied thermal science there. And very recently, he conducted a life cycle assessment project at IRAP in France in collaboration with Didier Barret and Jürgen Knodeseder. And with that, I leave you the floor, Andrea, up to you.
Yes, hello. Can you see my webcam now? Perfect. Yes, thank you for the introduction, Veronica, and also thank you for the invitation to this webinar about sustainability of the space activities. Today, I will talk about life cycle assessment and the life cycle assessments we have conducted on the X-IFU experiment, and also the results that we have obtained from this. And as you said, my name is Andreas Wolnievik, and for the most parts of this year, I've been stationed down in France at IRAP, where I've been working from beginning of 2024. And this has been in connection with Jürgen Knodeseder and Didier Barret, who's been working on this LCA for much longer than me. They basically started working with this together with for the first version that was carried out a couple of years ago, and the report of it was released a couple of months ago. So first off, I will begin a bit by going through what life cycle assessment is and why it's important, and some of the different also core stages you need to understand behind it. So I will just, this is probably a picture most people recognize. It's the planetary boundaries, and the basic idea behind this is that the environmental scientists were basically wondering if human activity destabilized the Earth system, since it's been basically stable for the last 10,000 years. And are our activities that we are contributing with destabilizing this stable period? And the answer they found was that yes. And after that, they basically identified all the different boundaries that are shown here in the picture, where you can see that 3 out of the boundaries has basically been, are still in the safe operation stage, and 6 out of 9 of them has already exceeded the limits. And how the space sector, 2 examples of how the space sector are influencing in these different categories are, for example, the first one is the novel entities and waste, where space mission basically contribute to the creation of different novel entities. Everything from chemical residues, from rocket fuels, to microplastics, to different orbis debris. And another one is also the CO2 concentration, how space instruments and rockets are basically emitting a very significant quantity of greenhouse gases, either by different ground activities, which I will discuss today about our experiment a bit, and also from launches, where, for example, black soot is released, and this is something that can contribute to, for example, ozone depletion as well. So first off, we have witnessed a very large growth in the space sector in the last, basically in the last years. And here in the picture, you can see the orbital launches by year and country. And it basically started in 1957. And you can see the curve now, how it's basically been increasing for the last couple of years. And this is something that if it is going to continue, we need to basically have, basically need to have different ways of dealing with the impact these activities have on the climate. And however, while our ability to assess and utilize the space is evolving, there still remains a very substantial gap in our understanding how these activities basically impacts Earth, especially some of the upper atmospheric activities from rocket launches where space missions are having some direct impacts. And for this, there are some different tools that has been developed. Some of them are like material flow analysis or carbon footprinting. And the carbon footprinting, for example, is looking basically at the CO2 emissions. And the one I will discuss today is only the life cycle assessment, and I will try to really go into the different advantages you can contribute to this tool. So to start off, what is life cycle assessment? Basically, life cycle assessment evaluates the environmental impact of a product, process, or service through the entire life cycle. And it's a multi-phase and multi-criteria tool, which is, you can see in the picture here to the right, how it's a multi-phase that you basically look at the raw materials, everything that comes in for creation of the product, the raw materials from extraction to the manufacturing, to the different distribution logistics around it, and also the usage period and the end of life. And for the end of life, it's usually for a rocket, for example, that would mean the deorbit. And it was basically a concept that was created in the 1960s, and it got some international standards in 1997, which you can see here is like ISO 40040 and 44. And this one basically provides you with principles and frameworks, and also the requirement and guidelines in how to conduct a study when it comes to LCA. And it has since also evolved and expanded to include different methodologies and different tools in order to be able to assess the environmental impact of products or services as complex as some space systems. And then we also have the steps of how you conduct an LCA study. First off, I gave you some background, but here in the picture, you can basically see the life cycle assessment framework for how to conduct it. It's basically put into 4 different steps. The first one is the goal definition and scope definition. And you also have the inventory analysis, the impact assessment, and something that is important to notice, like it's also the interpretation, which is iterative between all the different stages. So this is not something you follow these from one to the next. It's a lot of iteration between the different steps when you go back and forth. So in the goal and scope, this one basically involves clearly trying to define the purpose and boundaries behind the LCA study and specify the goals and the intended application of the study. While if you look at the scope definition, this one is more talking about the system boundaries, the impact, a bit more about what the impact categories you want to have assessed is, and some other similarities. And then you come to the life cycle inventory analysis, and this is basically you're trying to compile all the inventory of different inputs and outputs like the materials and energy as inputs, and then you try to also find out the different outputs in forms of emissions and waste. And all of these are basically associated with the different products and processes through the life cycle. And this is when we carried out our study, this one was by far the most time-consuming step, as it includes collecting all the data basically of the model, of all the surrounding flows. So you have to put a lot of effort into this step. And then when you come into the last step, is basically the life cycle impact assessment. This is when you evaluate the potential environmental impacts, which is associated with the inputs and the outputs from the inventory analysis. So here, this steps basically involves trying to quantify and involves like quantifying and characterizing all the different environmental burdens, and you use different impact categories such as global warming or acidification or resource depletion for doing this. And something I also want to point out as well that is different from when you conduct an LCA on space projects in comparison to some other industries is that for many cases, it's a very low production volumes when it comes to the different models that you carry out for a project. For example, you have the engineering model, qualification model, flight model, but these models basically are created with, in many cases for instruments, space instruments, with very small quantities of material during an extremely long time period of maybe 20 years. So this leads to, in many cases, that you have a very small footprint from the different products in the space assessment, but you get a large footprint instead from, for example, that you have a very long development cycle and long testing periods. For example, there are some very specific testings that are involved in space activities when you do have space instrument, everything from having clean rooms that has to apply to certain criteria so you can apply it for space applications, and also you have different testing like vacuum or thermal, and these tests can also be carried out multiple times during different models, and this is something that contributes a lot to the final footprint of some of these experiments. And in this second part, I will explain briefly around the two handbooks that are basically available. The first one is the ILCD handbook, and the second one is the ESA handbook, and a bit of just quickly how you can use this when you do a study. And the first one is the ILCD handbook, and this is basically a general guide for life cycle assessment, and it provides like a common basis for life cycle data and studies, how to conduct it. And it basically means that it's helping the user and guides the user in dealing with different environmental decisions, and can help in support related to the services, products, or waste management. And then we have the ESA handbook, which is basically more for space applications specifically. It comes in very handy when you try to understand space applied LCA, as it brings up many of the issues and how to deal with these specific problems, which is very relevant for the space industry. Some of them I mentioned in the last slide, like testing or long development cycles. And this handbook was first published in 2016, and that was the first version, and I think they're working on the second version now, and that one is going to be released in the near future. And just some short info about this handbook. It was basically published by the Clean Space Initiative, which is a program by ESA, and they are trying to minimize the environmental impact of space activities, both for Earth and in orbit. So it's a very good initiative. And in this picture here, you can see when you carry out life cycle assessment, it's an example of how a breakdown can look like. In the picture here to the left is how they carried it out for Ariane 6, for example, how you have one launch of Ariane 6 is the functional unit, and then everything on the way towards the end that is included to carry out this study. In this one, for example, they excluded some of the early stages, like the research and basically the feasibility phases, and they put more effort into the launch campaign and the different launch disposal and flight liftoff associated activities. So it is fairly difficult sometimes what you should include and what you should exclude. So this is something you really need to put effort in when you put up the initial boundaries of your and scope of your study, what you want to include for your study, basically. And here in the right, you can see also a breakdown of what are included in what can be included in some of the different stages when you do a breakdown for an LCA. For example, for the feasibility and preliminary definition, you are mainly having office work and traveling. And then it's a bit more heavy when you get into the detailed definition, when you try to also include everything that has to do with creating the models or rocket and all the testing and transportation. So this one is, in terms of when you carry out an LCA, one of the harder steps to get all the different inputs for the software you want to use. And then I also want to mention that there are very many different indicators for LCA, and there are basically, you have the different midpoint indicators, and these measures the environmental impact at the intermediate stage in the cause-effect chain. And then you have the endpoint indicators, and these ones are measuring the environmental impact at the end of the cause-effect chain, basically focusing on damage to the overall areas of protection. So here in the picture, you can see how it's represented, how you have different midpoint indicators, inventory list, endpoints, and from the inventory list, for example, you have some of them connected to the climate change, which are, in this case, N2O, NH3, CH4. And then for the endpoint indicators, you have all these different midpoint indicators directly linked to these. And easily described is basically that midpoint gives the scientific detail on the cause of environmental impacts, and they are very useful for identifying specific areas of concerns, while the endpoints are providing a more simplified view of the overall damage and are basically, you can find key areas of protection through these. And they can be a bit more beneficial when it comes to communication and decision-making for LCA. And then we have the part 3. I will talk a little bit about the different software and databases for LCA that are commonly used. And for our project, we use SimaPro, but it has upsides and downsides, this software. It is having a lot of good databases and a lot of good processes and methods that you can use for this program, but it is also very expensive to get, which is the downside. So if you want to start with LCA, they basically have OpenLCA, which is, this one is free to use, but it requires, in some cases, specific databases where some are free and some are not. So you are still limited when you use this. And another big database is also the Gabi one. This one is used, I think it's by Airbus a lot. And when we carried out this project, we used SimaPro, as I mentioned, and for this, the 2 databases that we were involved with was EcoInvent and the ESA database. And for this, I think it's important to understand what foreground and background systems are. And here you have like the foreground system is basically includes all the different processes and activities that are directly controlled or influenced by the entity that is performing the LCA. And then this one represents basically the specific parts of the system that is being analyzed. And for us, this would be the space instruments of X-IFU. And then you have the background system, and this one is represented by the different process and activities that are outside the direct control of the entity. So this is like what is outside of our control as X-IFU. And these ones basically involves the two databases that I mentioned. We used the ECOIMED and the ESA database. And now in this part, I will give a more detailed overview of the experiment and a bit of the, not concerns, but a bit of the bullet points for what was important for us when we carried out this study. First off, you have here is some information about what the X-IFU is and what the purpose of it is, what it wants to basically measure when we get it up in space. And it's basically the concept behind it is that it's a high spectral resolution. It wants to combine high spectral resolution with high quality imaging, and will be able, by doing this, to capture different images of astrophysical objects in which each of the pixels in the image will basically provide a full spectrum containing information about these different objects. So they will be able to extract information about the formation and evolution of some of the large structures of matter observable in the universe. And for instance, they will be able to measure some of the abundance in different elements, everything from oxygen to iron to tin, within some of the bigger galaxy clusters. And for this, there are some very impressive instruments that are basically developed by X-IFU, and one of them are the transition edge sensors. And these are basically sensors that will operate at 50 millikelvin. And this is to be able to do some delicate and really this is done by a very complicated cooling chain. And it's been studied since 2014 for operating aboard the Athena X-ray Observatory for ESA. And it was basically designed to address the hot and energetic universe science theme that was selected. This was something that was selected in 2013. And in 2022, the X-IFU entered the SRR. And after this, it went into a reformulation stage, basically. And this is one of the reasons why we carried out the LCA, as a lot of reformulation to some of the different systems were implemented. And here to the right, you can see a very interesting picture of what it might look like, one of the images that it will be able to produce in the future, with all the temperature variations here creating the image. And some aspects about how big this project is, that we basically have over 300 people that are active on this experiment at the moment. And it's estimated that already more than 5,000 people has been working on this from 2016 to 2023. And this is very important for when we conduct this study, as we are also looking at a lot on the footprint of the FTEs, like the different consumptions from facilities and commuting and everything. So, and the launch campaign, it's expected to be in 2036. And we have on this project 13 countries that are involved. So it's a lot of participation especially from France, Netherlands, Italy, United States, and Spain. And now I will come into the breakdown of the X-IFU, how we conducted this study and everything that was included from our side. First off, I talked a bit earlier about, I gave a quick example how the Athena 6 breakdown was made, and I will now present a bit of how we did the breakdown for X-IFU, as this one is we are basically focusing on an entirely different area, mainly a space instrument instead of a rocket. So what we have included in the timeline were basically the early stages before the launch of operation. And we broke it down into different flows, which you can see here to the right. Everything we included: the personnel, the traveling, everything about the testing, the model and logistics, and different equipment. So for the first flow that we included when we carried out the data collection of this study was the models and logistics. And this one is basically, here we wanted to include all the data of the different models, like the flight model, the different engineering models, the qualification models. And the main data that we collected here are for basically different materials and processes and end of life of these different models, what is happening in these different stages. And one of the issues we basically faced here was that many of these systems are still in some preliminary stages. And because of this basically creates a lot of uncertainties in what different processes and material they are expected to have in the future, as these models might not be created in a couple of years. They are still being developed. And then we have the second flow, which is the equipment flow. And in this one, we basically added the equipment that supports the different testing models. Everything from cryogenic test benches to data equipment and different specialized tools that are necessary for carrying out different tests. And this is something that for the first version that was published recently, this was not included. And that was one of the reasons that we wanted to include it for the second version. We wanted to see how much are the different equipment behind the experiment also contributing to the final footprint. And then we have the third flow, which is the personnel. And this one here, we basically took direct data from different systems, like we tried to gather how much people are commuting inside the systems, the different facility electricity usage, how much heating is going into the facilities, the water usage, and we used all of this to create our model in the software. And here to the right, you can see basically a breakdown of the different inputs that we then use later for creating the model. And then we also have traveling, which was, when we looked at the results, this was one of the bigger impacts. And this was basically everything that was, all the traveling flow that was for different meetings or conferences or consortium meetings, basically all traveling involved to the X-IFU experiment from the different systems. And then the last one is testing. And this was also something that we noticed in the results was a very big impact. Because in space projects of this sort, basically you have testing is very specific. Unlike other industries, each component in a space system can be tested multiple times in the different stages, everything from development to qualification. And these tests can be very long and very, very also resource intensive, and can require some specialized facilities that are also hard to, the standards, or like the credentials for these facilities has to go to a certain degree for it to be applicable for space instruments. And for this study, here in the picture, you can basically see a breakdown of X-IFU, and you can see all the different systems that we had for our study. We basically identified 23 different subsystems that you can see here. And it's everything from the DWAR units to cooling chains that are here, to the filter reels, to the different onboard computers. And these different subsystems, after breaking them down into these 23 different subsystems, we then try to collect data from each and every one of them. And this breakdown was basically made, as you can see here in the picture, how we split it into the personnel flow, the traveling flow, the logistics, testing, equipment, and models. And then we try to find all the different inputs and outputs from these systems, like from the personnel, we try to find out how many people are working on this in this system and how many people are expected to work on these systems until 2036. And we also try to find different commuting data, the different facility data, different heating data from the facilities as well. And then one of the larger footprints, as I mentioned, was also the traveling. And I will not go into this, but you basically define a bit more here about the traveling as well. If it's long travel outside of Europe, or the travels more inside Europe, or people traveling more by train, or what kind of traveling is going on in the system. And this was also estimated until 2036 for each and every system. And then we basically, as I mentioned, we had two versions. We had the first version that was published recently, and now we had been working on the second version. So basically we used some of the data we really put a high focus on in the updated version was regarding the clean rooms and the traveling, as we had seen a large footprint in these categories. And we had seen from the first results that these were some of the hotspots of the experiment. And I also want to just define quickly what some of the main goals related to this second version of the LCA study was, because this is very interesting. It's very important that you have a good setup of goals and boundaries in the system. And the first one was basically reformulation, that it had been, the experiment X-IFU had been reformulated in 2022. So there had been a lot of changes to the system because of this. And we wanted to have this accurately shown in the model as well for the results. And also we wanted to carry it out in-house, since the first version of the LCA was carried out by a company. We did not have always the kind of insight in what was happening in the different sections that we wanted. So we had the advantage with the second version that we had much more control over the results, over the analyze, understanding what was happening behind everything. And this basically allowed us in some ways to go beyond the work that had been performed so far. And also, we wanted to put up different alternative scenarios when we could implement different changes and see how this affected the results. Everything from changes in travel to changes in different facilities. And also maybe work on future iterations when we have more data available, that we maybe carry out an LCA on X-IFU in a couple of years as well. The last part here is I will present some of the results that we got from the first version and the second version and compare it a bit and talk about what is basically happening in our instrument. In this graph here, you can see this is a damage assessment graph and the results some of the results we got from the first version. And here on the y-axis, you can basically see all the different impact indicators that were used in this method, the EF 3.1, and what it and how big contribution it had to the experiment. Here on the x-axis, you can see the percentages on the contribution from each of these different flows. We have the XM and FM, for example. These ones are represented by all the models of X-IFU, all the different materials and processes and end of life, all the steps of the models. And we also have the transportation, which is basically the logistics, and we have the assembly, integration, and testing, which is the purple, and office work as the brown, and all the different traveling inside the experiment, which is the light green. And it's also important, I think, to understand a bit about these different indicators, what it means, because this is one of the fun, or not fun maybe, but one of the important things when you carry out an LCA, that you have so many different impact categories. You don't only look at the climate change, how this one is affected. You also look at the ozone depletion, which is basically evaluating the different substances that degrade the stratospheric ozone layer, and you look at the ionizing radiation, photochemical ozone formation, particulate matter, toxicities, acidification, which basically assesses the emissions that lower the pH of different soils and water bodies, and the different eutrophications like terrestrial, marine, freshwater. And you also include something that you see the models are contributing to a lot here, which is the resource use, minerals and metals. And this one is basically, this flow helps you in, this one considers the depletion of different natural resources. And in this graph, you can also see what we got from the first version, mainly that the testing was a large contributor to the footprint of, if we look now at CO2, or climate change, it was a large contributor to this flow. And this was mainly due to, there was a lot of clean room usage for this experiment, a lot of footprint from the different clean rooms especially, and also some very heavy test equipment that was carried out for very long durations. And then if we look at the office work, this one is mainly dominated by the commuting of the people working, of the different facilities as well, the different heating that goes into the facilities, and all the electricity to run the facility. And then the last one is the light green, and this one is the traveling. So these three were basically, in most of the categories, you can see how these ones were mainly the dominant flows. So because of this, we really wanted to pinpoint this for the second version and understand everything behind it again, and get also more detailed data of why this came to be. But also an important factor is to take into consideration is that you have a very big impact here in the resource use, minerals and metals, from the models. They are not contributing to the climate change, but as I mentioned, this is one of the perks with using these many different impact categories, that you can see the specific footprint in other categories, like here for the models, where they are contributing a lot more. And the transportation, for example, that was something that we noticed when we did the first study, that it did not have that much impact. So that was a reason that we did not put as much effort into this one for the second, regarding collecting data, for example. And in this graph, this is one of the results graphs as well, and it's representing the weighted results of our assessment. And here on the x-axis, you can see PT, and this is points. These points basically represent the relative environmental burden, and are often expressed in the environmental impact of an average citizen. So what it means easily is that for climate change, for example, you have an environmental burden of a citizen, which is basically equivalent, when you use this method, to 7,500 kilograms of CO2. So when you see a single point here of 3,500, this means that this is basically the environmental impact of X-IFU systems is considered in this study and corresponds to the annual environmental load of 3,500 humans. And here to the right, you can also see some basically how they weight these different categories of basically they have experts that put these categories into importance. Like for example, in some of the methods, they put climate change as higher importance. So you get a spike in the climate change when you do the method. While, for example, resource use, they don't see as important, and the weighting factor for this is therefore lowered, and you can get a reduced result for this factor then instead. And in this picture, it's also important to point out, I want to talk about uncertainty analysis. This is basically a way of showing how accurately we think our data is for each of the systems. You want to basically reach a low uncertainty, as this would mean that the data you have collected is correct, and also how the data from the databases are represented well by these inputs. And as you can see here, the uncertainties in total for many of the different environmental impacts per subsystems all of them are indicated by black here. And for the first version, we had an uncertainty range for many of the systems from 25 to everything from 25 to 70%. And this was a lot depending on the quality of data collection and the maturity level of the system. As I mentioned, a lot of the systems when we did the study are still in the preliminary stages, which means there are a lot of uncertainties behind the data we collect and get from them. And it can be a bit difficult sometimes to understand when you look at the graph what the final footprint is of the experiment, as it's the one I showed now, it basically showed the percentage. But here is a good representation of the data we got from the first version of all these different impact categories, where we saw a very big footprint coming from the climate change. Mainly it was 25,000 ton CO2. And these values we wanted to really understand and compare to the second version then to see, basically to see if we managed to get a better model and how this would also affect then the final footprint in the results. So for the second version, you can see here in the picture, we basically identified the 23 different subsystems that I mentioned. And out of these 23 subsystems, we got updated data from 17 of them. And we also added, because of the reformulation of the project, as I mentioned, we had some new subsystems that was also included in this study. Like we had a cooling chain that is developed over by in America, and we also have the D-work cryostat that was currently not in the study we carried out. And we basically got new data from all these different subsystems for the new model, apart from 2 of the systems, which was something we were very happy about in general. And here is a comparison between the results that we got from the first version and the results that we got in the second version. In the top, you can see the first version where we had a very large footprint coming from the testing and the office and traveling, as I mentioned. And then when we compare this to the second version that we carried out, the first iteration, you could really see, for example, here you can see for the traveling, how this section had been reduced. And this was mainly due to that in the first version, they were looking at the pre-pandemic case for how traveling trends were. And when we did the second version, we really tried to put emphasis in trying to understand how the traveling trends of X-IFU had changed, how much had people reduced the traveling. And we did see that after Corona, people had reduced it, and there was more meetings being held online. For example, there is a consortium meeting that is being held during this week online that was sometimes in person before. So that was a very interesting detail we saw in the results. And we also got some differences when it came to the testing. As this one, for the second version, we got a much lower value for the testing for climate change. And this was mainly due to that we managed to get more details and more direct data for this category than we did for the first version. And we also, something that we got a bigger footprint in was the office work. And this was because, as I said in the previous picture, that we had a lot of new subsystems added to this iteration, and we also got more precise data about the FTE included in the systems. So in many cases, this meant that the values went up. So this also got represented in the final results, as you can see here. But as a final results, when you look at basically all the different categories from the first version to the second, we did notice a decline in the results in basically all the categories, which was, this is basically what we're analyzing now, as these results we just recently got done with the model. So we are analyzing everything at the moment. And it's also some interesting observation is that you can see how we did not have the equipment for the first version, and this one we implemented for the second version. And it is similar to the transport when we got the results, that you can see how small the impacts are from the equipment. This is something that I think we expected the impacts to be larger, but we basically just had a very small impact from the equipment, and this one was in research use, minerals and metals, and it's basically not even applicable for the other different impact categories. And here I have a picture where I am comparing directly the climate, the CO2, the climate change footprint, where you can see the bottom graph here is represented by the first version that we carried out, and this one is from the second version. And it is a bit like I talked about, that we can see a reduction here in the traveling and in the testing, but you can see that it's been an increase in FTEs instead. And some final remarks also about when you look at these results is that in the picture here to the left, you can see the different footprints from, if you look at 1 kilowatt when you use this software, when you use this database, that basically 1 kilowatt for different countries. And as you can see, the difference is quite large. And this is because it depends a lot on the different in energy mix when you use it. For example, some countries has a much higher green energy mix with more wind, with more water or solar power, compared to some other countries that are more dependent on coal or nuclear energy. And when we did the study, if you took, for example, a look at France and compare it to the US, you can see that one kilowatt in France is basically, or 5 kilowatts in France is basically equivalent to 1 kilowatts in America. And this was also something that was important that we had to take into consideration in our results. Basically, how large parts of the CO2 footprint come from these different facilities and clean rooms. If we were, for example, to change and reduce the testing in France, by 50%, this would maybe still not be as beneficial as if we were to reduce the testing by 15% in the US, as the US electricity mix brings such a boost to the CO2. And then also, another key point is the evolution of different data sets. Basically, when we first did the study and we compared the different results in the second study, we saw that some of the large changes in the impact categories, and two of them were mainly ecotoxicity and ozone depletion. So because of this, we wanted to really understand how this came to be, and we did a replica of some of the systems from the first version with all the data used back then. And even so, we did get very large differences in the results, even with the same input data. So we sat down and we really tried to understand how this came to be. And after setting up a meeting with one who is expert in the field, we did figure out that the evolution and changes in datasets can vary to a very high degree. And for this example, the ecotoxicity had been re-evaluated in the earlier version and therefore reduced a lot. And that was something that we then saw almost exclusively in the results, that the ecotoxicity, we got to 1/4, even though we had similar inputs for the second version for some of the categories. And my point is just that it's sometimes hard to see all the background work which is put into the data sets and the methods. So you must be very careful when you do comparison of studies that's been done with years apart, even if it's on the same instrument. And some final conclusions and remarks is that for X-IFU, we do see a very high potential in reducing our impacts and understand where our impacts come from because of these studies. And changes has already been made, especially when it comes to traveling, that this is something that Didier Barrett and some other people in X-IFU were dedicated about, that to change the different travel patterns. And we saw this as some positive results in the second version for the results that we had been able to basically reduce the footprint in traveling. And another key point, I think, is when it comes to that data gaps, there are some substantial basically gaps in the data, particularly for emissions at different high altitudes and for different non-CO2 emissions like black carbon and alumina. And as a result, this basically leads to the models having, in some cases, some limited precision when they are trying to estimate the long-term climate impacts. And I think overall, there have been probably too few targeted LCA studies on different space projects, and the field is still developing a lot. So I think there are a lot of uncertainties still in how this is carried out and the different methods behind how you should carry out the study. So in the future, hopefully there will be a lot of more comprehensive LCAs, and this is needed to provide a very clearer picture of different space instruments or rockets, how these basically contribute to the environmental changes. So I think that was basically it. And yes, thank you.
Thank you, Andreas. This was very highlighting, very interesting. You set up a lot of subject. I don't know if there is any question from the audience. There is no question right now in the question and answer tab, but if you want to ask a question, you can raise your hand and hello. Well, I have a first question. So suppose we have a M-class mission that we are preparing. We are preparing the proposal, so we are at the very early stage. And so we would like to consider doing an LCA analysis from the very first beginning. What would be the first resource you would recommend to look at? For example, to write the system breakdown, to evaluate which part you are going to analyze. So you mentioned the ESA handbook. I mean, what are the resources that we should first look at if we want to begin an LCA analysis?
Yeah, that's a good question. I think like the first steps would be, I would recommend, is to go through the handbooks a bit, and especially the ESA handbook, and try to get a bit of understanding, but also try to jump into some of the softwares like OpenLCA and try to really get hands-on experience, so you don't get stuck too much in theoretical stuff. You should try to really put up some models yourself and try to see the results from this. But as a starter, I think the handbooks are a good start. And also, as you mentioned, try to understand the different goals of your study, what you want to include, and put this into context early on.
Maybe if I can add a little bit. There is in fact the general problem that to make a full life cycle analysis, you have to know already quite in detail what you want to build. But very often, if you go for a new mission, you don't know yet in detail what you want to build. So there's in fact quite some dynamics actually ongoing in what is called simplified life cycle analysis, which is at the end not so different from a big spreadsheet in Excel, where you just fill in maybe 10, 15 different parameters, the size of the mission, the launcher, and so on, the orbit that you want to use. And this gives you then already some first impact assessment. ESA is currently working on these kind of things. Also, the CNES has already a tool, so the French Space Agency, that is at this stage. I think it's already available, or it's becoming available very soon. Just to break the circle that you have to do this analysis very early on if you want to impact at the end the design of your mission, because if everything is already set, then it's very difficult to make changes.
Okay, thank you. There is a question by Cyril Panetier. Did your LCA enable to make decisive choices to decrease the instrument damage score? How much do you think you can then decrease it? So here you measure, but how much can be done to decrease the damage? Well, you mentioned the travel, of course, but apart from that.
Yeah, that's a good question. I think some of the key areas where you can really make an impact in changing is, I think it is in the testing and the traveling, but the testing is probably the biggest one, where you can reduce it from the different clean room usages. For example, you try to reduce the different, also you can look at reducing the time of the different test campaigns, and you really try to you try to really plan everything more in advance when it comes to the testing. I'm not sure, like, yeah, maybe Jürgen can answer a bit more on this. I have not thought about it, like I have to think a little bit about it maybe.
Yeah, it's definitely, I mean, the testing that can be done quite a lot. I mean, very often, if specifically for a complex instrument like X-IFU, where you have many different subsystems, everybody is doing testing at subsystem level, and you integrate and you test on the system level, and you integrate more, you test again and again. So here you can rationalize certainly a bit how you do the testing. But then you can also work, for example, on the facilities themselves. I mean, there are examples where, for example, the energy use, at the end it comes down to energy use in clean rooms. Specifically the change of the air in the clean rooms. You can gain quite a lot in energy use, and so have more efficient test facilities, and then maybe, for example, decide to only do tests in efficient test facilities with low impact and so on. So this is certainly also an interesting area of improvements. And I would also say for the what Andreas called the FTEs, or the manpower office worker category, very simply, I mean, if for your offices you can reduce the impact, for example, biothermal insulation of the building, by using more efficient whatever appliances, then you can also gain in this category, which has also additional side effects that globally the impact of the office space will be reduced. But by how much? Because you asked by how much you can decrease. That's always a tricky question to answer. So far, other studies that I've seen, it's always in the 20–30% range. Maybe you can do a bit more. Probably the most optimistic scenario, it's maybe 50%.
Okay, thank you. Is there any other question? When you are going to publish your second paper, will you try to be a bit also pedagogical for the people who will try to do something after you and say, okay, this is how we've done things, and present the thing how it should be done? Maybe not exactly in the way of you have done it, but okay, if somebody reads your paper, he can see, okay, these are the steps that I need to follow. Like if you have this view of having a document that can really serve other people to carry out an LCA, that would be really nice. But I guess this will be the purpose somehow.
Yeah, it is interesting. Like, we are still debating of what to include in the report, but in the first version there was a lot of description surrounding how the study, a bit more of how the study was conducted. And I think for this second version, it will be more about presenting mainly the results that we got. That will be the main focus, and also try to also implement alternative scenarios. As you talked about in the question, we want to put up alternative scenarios where we can see some reduction in, for example, in the testing or for traveling. And we also want to try to put this into the model, these scenarios, and see how this affects the results, like the end results. But it would probably not be that you can replicate the work from the paper, no. Then you would probably need a bit more information that we will provide there.
Okay. Okay, so the two papers, the first one and the second one, can be read together. So in the first one, we have more explanation, and in the second one, all the change, the updates, etc. So Thierry Dudoc de Witt is asking another question. One problem we face is that such LCA are perceived by some as a threat to the project. What is your experience of this? How do you deal with such a reaction? So were there any resistance to doing such type of analysis, saying, okay, but then we put in question this very instrument?
Yeah, maybe Jürgen want to answer this. We have discussed it a bit, but I think it's one of his stronger topics. Like he's
I think,
working.
Andreas, you can also talk a bit about your experience because you collected a lot of data from the people. So, I mean, was everyone equally willing to give data, or were there some people reluctant to give data? I mean, how was the data collection process going?
Yeah, that's a good point. That's something that we tackled when we had these meetings with all the different subsystems. That you felt some people were not that interested in getting the data, so you could really see this in the template when we had it collected, that it was, for some of it was very few details, while some of them you could really see had a lot of details when it comes to the different processes and, for example, materials behind the different models. So I think to get like a consistent study, you basically need, it would be preferable to get the same kind of details from all systems. But that has also to do, then you also have to have people that are having the same kind of interest in these kind of studies. And that is something that we experience that is not always the case.
Yeah, and maybe to add on this, I mean, you maybe have recognized that one of the key persons here is the PI of the instrument, and I mean, all this initiative comes from him to do life cycle assessment. So somehow he imposes this on his consortium, and of course, not everybody is swimming or running at the same speed. But they have no choice. And I think that's really, I mean, that's somehow the optimum situation that you can have. It will be very difficult to do such a study against the direction or the PI or whatever. You cannot do this underground because you have to access a lot of data, a lot of information, and you have to make sure that basically everybody plays the game, even if some people are maybe more reluctant than others.
I'd like to thank again both of you for this webinar and for this very interesting and important work. We'll just like to mention that this will be also posted on the YouTube channel of E-SWAN, and we have another webinar that is planned for the 4th of December on the experience by the French community in astronomy and astrophysics about the reduction of their carbon footprint as a whole for all of their activity. So the webinar will be in 2 weeks' time at the same time. Okay, with that, thank you all, and see you soon.